My guest today is Professor Claudia Maraston, who's Professor of Physics at the University of Portsmouth. She designs models for the calculation of spectro-photometric evolution of stellar populations. Welcome, Claudia.
Hi, good evening, everyone. Good evening from
Yeah,
the UK.
thanks. Yes, it's late for you. Yeah, thanks for doing this late after dinner.
Absolutely.
Um, so I got some of your papers, and we want to go through them. But we probably want to start at a slightly higher level. So let me get into one paper, and then we can go from there. So the first one is strong spectral features from asymptomatic giant branch stars in distant quiescent galaxies. So you say here dating the ages and weighting the stellar populations in galaxies are essential steps when studying galaxy formation through cosmic times. Evolutionary population synthesis models with different input physics are used for this purpose. Moreover, the contribution from the thermally pulsating asymptomatic giant branch, TPAGB, stellar phase, which peaks for intermediate age, zero point 0.6 to 2 gigayear systems, has been debated for decades. Um, so what was the debate about? Were people saying these things don't exist, or what was the debate?
Yes, excellent questions. The treatment of this particular stellar phase with this name was actually the subject of my PhD. It turned out when stars, like even our own sun at some point in its evolution, enter this phase in which two central burning are active at the same time, and they imply a pulsation of the star with different excursion in energy that is emitted, that modeling is very complicated. Theoretically, because it takes long computationally because of this uncertain input physics regarding the burning in this pulsation mode. And therefore, different schools in the world have performed different modeling. And 20 years ago, I published my paper, the one that is at the core of these observations, making quite a strong prediction on what could be observed in very distant galaxies. So the debate is about how much this particular part of a stellar life would contribute energetically and whether you could actually detect it in real galaxies. That's the debate.
And if I understand this correctly, JWST data shows these things exist.
Yeah.
And so before we get the details of this, Claudia, so for the public, I'm going to start the basement. Stars are those fusion instruments that convert hydrogen, that fuse hydrogen into helium, releases a bunch of energy, and there is a lot of them, and we have one very close to us, and that's why we live, I suppose. And so when you say population of stars, so now these things sort of assemble into some group of things, and sometimes they're galaxies, sometimes there are other things. So when you say population of stars, what do you mean?
Yes, I mean an ensemble of stars that can be homogeneous in terms of the chemical composition, like, for example, the one of our sun, but can also be different. The reason why we use the term population is because galaxies, big galaxies, and those that are the interesting bit in this, are actually made by different populations of stars, and it is only thanks to the stars that we can see them, because stars are the light emitters, and galaxies are huge containers full of stars. So from the theoretical point of view of calculating a model, and this is what I do, I regard galaxies as a collection of population of stars, and we go from there.
So could you describe? So I know that stars go through just like humans a
Yes.
life. of their own. And when we look out, the universe is approximately 14 billion years old, I suppose. When we look out, we see all sorts of, we see old people, we see things, we see young babies just being born. We see all sorts of things there, right? So, and they all have different characteristics, obviously. Um, and so, how do we? So, do we have a classification system for these large number of? How many galaxies are there? Like 100 billion galaxies or something like that?
Billions, yes. So that's a rough estimate. Yes.
And 100 billion galaxies, and approximately how many stars in a galaxy?
Yes, so in our own Milky Way, there will be 100 billion, roughly. This is an average based on calculating the number of stars as if they were like our sun. There will be more of smaller mass stars and less of higher mass, but on average is this 100 billions. Our galaxy is not the biggest galaxy in the universe, and you can find actually galaxies that are really order of magnitude bigger, and they will contain roughly proportional more stars. So in general, we have a huge population of stars, and as you really correctly say, I always use this analogy. Stars, as people, get born, age, and die eventually. And the light emission, which we call the spectra, the distribution of energy as a function of wavelengths, will actually benchmark this evolution through the age. And therefore, we can calculate the type of model I calculate in order to actually perform what is crucial in astrophysics and cosmology, which is determining when galaxies form, their age. As you said, the universe we think is 14 billion years. When did the first galaxy form, but also when our own Milky Way form, we can actually obtain this information from the population of stars in those galaxies.
So one of the metrics that you use is metallicity. So let me see if I can understand this. So when the star is very young, it's basically fusing hydrogen into helium. And when it goes through its phases, I guess at some point it runs out of hydrogen and start fusing helium into other things. And so when the star gets older, then you could have higher concentration of other chemicals in there. Is that the way to think about it, or no?
Yeah, so in general, you will have an initial composition, initial metallicity, which is the one of the gas cloud out of which the star forms. As you perfectly say, a newly born star is quite hot, and all this chemistry will be fully ionized. Namely, it's harder to actually distinguish what is in the envelope of the star. But when the star ages, it gets colder, the temperature is lower at the surface, and then the elements will be the same, but because the temperature is lower, they get back to their state, and we can see the lines emitted by the elements. And that's how we actually deduce their composition.
Yeah, so could you talk a little bit technically about the spectra analysis? So we're looking at the light emitted by the stars.
Yeah.
And then we can analyze that light.
Yeah.
And say, there's so much iron in there or so much other stuff in there. So how do we do that in the spectral analysis?
Yes, so observationally, which is what the astronomers around the world which have a disposable telescope do, they collect the light emitted, so photons really, in a certain wavelength range that depends on the instrument that they have at disposal, which is called the spectrograph. In the US, there is the Sloan spectrograph that has done this history of collection of galaxy data, really, which is essentially an optical instrument. But nowadays, in Chile, at the Very Large Telescope, we can actually collect the light in the near infrared, and with the James Webb Space Telescope as well. So those are the... How do you make sense of the data? This is typical in physics. You need to have a theoretical model that actually mimic those emissions. So what I do is to use theoretical stellar evolution, so this information of how the stars passes through the phases, associate a spectral energy distribution to all these phases, and then integrate over a theoretical population of stars with arbitrary parameters. That gives me a series of models that I compare to data.
Compare to data. So you can fit the model to it. But I was thinking more mechanistically. Iron, for instance, I would imagine absorbs some wavelengths. So we're going to see some sort of troughs or peaks in the spectra, right? Is that how we determine that?
Yeah, that is perfect. There are two situations that actually I was discussing with the student this morning. The star can be very hot and still embedded in a region of gas, the gas out of which they form. In this case, the photons emitted by the stars will ionize the gas, and what happens is that we see a spectrum in emission, so with peaks of energy that is emitted. When this gas is dissipated, what you actually mostly see from galaxies is a spectrum in absorption. So all these wiggles that you've also seen in this paper testify the presence of certain elements, and correctly say, how do we know at which wavelengths they would actually manifest themselves? Well, the spectrum of elements is also known from the lab. So we know that, for example, certain line of hydrogen will peak around the 5,000 angstrom wavelength. Iron, as you say, is full of electrons, and there will be iron lines really all over the spectrum. But for example, sodium, which is something I'm currently studying a lot, that the main line of sodium that we use, it is located at 8,200 angstrom. Now, these are rest frame units of wavelengths. The galaxies that are very far away, we need to further take into account of the cosmological redshift that shift these wavelengths to the red, that we know it exists, but it's something we can do. So in general, we know that certain elements will give us certain line at certain wavelengths. And we know this from models.
Yeah, I didn't quite appreciate this. So when we observe a spectra from far out, we need to sort of adjust it for the expected redshift, right? So so almost any spectrum that we are observing needs to go through some sort of an adjustment filter before we can make any determination, right?
Yes, absolutely. And again, this is something one can calculate theoretically. This is something that people in the 70s started to think about. And there are two types of correction, and my models indeed take into account both. One is called the K correction, is a way of calling it, and that is just the shift of the wavelength framework from the observed system here on Earth that we call the rest frame, because the instruments are fixed on our planet, and the distance, space-time where the galaxy is. But there is another correction that is far more tricky, which is the fact that when we observe light that comes from the very distant space, for interpreting that light, we also need to go back in time. Einstein showed that space and time are connected, so we cannot separate that. It means the galaxy that emitted that light was younger. And this implies a different amount of energy.
Different amount of energy. So to make these corrections, we need to have an approximate idea of distance, right, where the light is coming from. Are we using a different technique for that or no?
So this is, the main technique is actually based on the same models that we are discussing, because the theoretical spectra will tell you, suppose, where the line of magnesium is peaking. And then this is at the rest frame, and then you find in the data a similar pattern of a line, And the distance in wavelengths can be straight correlated to redshift, which is the distance. Okay, so in general, you use, in fact, the spectra also to determine where the galaxy is located. In practice, with this type of model, you do the same thing. Nowadays, we live in the era of big data. So what actually astronomers try to optimize are, and I don't know much about those, so I don't want artificial intelligence sort of optimized method in order to get many redshift at the same time. But ultimately, it is still based, and this is amazing if you think about it. We know the distance of a galaxy if we can recognize some fundamental lines of element in those galaxies.
Yeah, so if you can use the patterns, I'm just making this up, Claudia, I have no clue.
Yeah.
Wendy Friedman was on the show recently, and she's struggling with distances and the expansion rate.
Yeah.
So if you mentioned AI, so if you feed the data to an AI thing, if there is such a thing, it can look at the patterns and it can say, this is sort of approximate distance that this cluster or galaxy might be.
Yes, it works exactly like this in recognizing similar patterns. Their limitation, which is really intrinsic, is the fact that the AI will recognize patterns that they know already. They have been trained on. This means that we can feed this machinery with a series of known models with known distance, and the AI will look into the actual data for similar things. It's harder with only AI to discover the unknown, because obviously being trained, they will only replicate what they know. Yeah. Instead, we humans have a head start because we can push calculation on models in regimes that we don't know whether they exist or not. And then the data will tell us. So I'm still a big fond of using astrophysics.
Yeah, so we have multiple ways to get to the possible answer here. So you say here the coexistence of oxygen and carbon type absorption features, spectral edges and features from rare species such as vanadium and possibly zirconium reveal a strong contribution from TPAGB stars. Yes. So talk a little bit about this TPAGB stars. So what's the redshift we are looking at? It's about 2. What's the redshift we are looking at here?
Of that very galaxy at the core of our Nature paper is a redshift of 1, so roughly 9 billion in look-back time. As we are in the paper, we have now other data from the James Webb Space Telescope where we go up to redshift 3. So what is the clue there that we said in order to understand how the universe formed and evolved, we need to have the ages of galaxies because they tell us as people, how old are they? So when did they form? Yeah. We need to use stars, but stars sometimes have temperature patterns that make them very similar. So what's the clue with the TPRGB that, as you perfectly summarize, it contains unique combination of absorption due to carbon and oxygen, composed in other elements like zirconium. I think this paper is the first detection of zirconium. We put tentative because we want it to be modest, but we think it is, in outer space at those redshift. So the advantage of trying to find this phase in distant galaxy is that it gives quite a precise age. The galaxy is going to be around 1 billion years old, not much less and not much more. So it's one of those cases in which, and that's called age indicator, we can actually be quite confident on our dating.
Are there any systematics we need to worry about, Claudia? I'm just making all this up, by the way. And so there's a lot of supernovae going on in the neighborhood, and the stars are sort of capturing, some of that metallic stuff and incorporating into their construct. Do we have to worry about that, or are they? That is not really. It's very immaterial in the large, grand scheme of things.
Perfect. No, of course, any generation of star that will have profited from the ejecta of exploding stars of the previous generation. And that gives you a different pattern. We are not going to worry about supernovae exploding at the time we view the galaxies, because this is a stochastic effect, which will have very little impact on our global spectrum. But in order to minimize this effect, we actually looked for quiescent galaxies. Quiescent galaxies means they have formed the vast majority of their stars, and that make their spectrum quite stable and really revealing of the stars rather than these stochastic explosions. So you got a perfect point, because in order to see this absorption in all their beauty, we need them to be stable and without the systematic, as you will say. And then you compare, as we said, with different models, and we have a collection there for many other colleagues in the world, but it turned out you actually need really to have those stars in that phase to give you that observation. So the observation was very constraining.
Yeah. So you need quiet and stable, as you say, systems where we can make more robust predictions or conclusions. So you see here in the abstract, these findings call for revisions of published stellar population fitting results as a point to populations with lower masses and younger ages, and have further implications of cosmic dust production and chemical enrichment. So what do you mean there?
Yes. So these interpretative models that actually we use in order to constrain the spectrum carry their consequences. It is the way we determine the age of the galaxy, how big the galaxy is, so their mass, but also how much dust will be involved in the evolution of the galaxy. That also depends on the details of the age. Therefore, as we find that one particular model works quite better than the others, and most of the results in the literature were instead based on the others, that means we needed to revise those results. Some may be roughly similar. We are actually doing that, but in general, we expect a change in the ages of the galaxies, and that has cosmological implications. When do galaxies form? A change in their size, and that impact also with dark matter and the evolution of it. So, and the chemical enrichment, because if we see already those redshift, those type of chemical elements, it means there has been quite a state of evolution of the chemistry of galaxies. So all in all, I have to cite the Heisenberg principle. These observations in themselves are not alive, but they start to make sense the moment you put a model on them. Because then the model will tell you everything on those galaxies. And what we are saying is that your knowledge, our knowledge, depend on those models.
Yeah, so astrophysics will continue, it feels like. And so this data that you're using here, because we have no JWST, we are still collecting more data, right? So this data set is going to get more and more robust over time?
Yes. So more than this data, the result is that we publish is robust in itself about what we have. And actually, this is the month we got the data. We have an ongoing program to collect many more of those galaxies with very high, we would say, signal to noise, so that we really see the spectrum very well, and the model becomes meaningful. So we are going to actually continue our analysis of much larger number of galaxies. And that will tell us a lot about the evolution of the galaxies, but also the characteristic of this interesting stellar phase.
So I want to go into another paper. So the MANGA Firefly Value-Added Catalog resolved stellar populations of 10,000 nearby galaxies. So you say here we present the mapping nearby galaxies at Apache Point Observatory Survey. I don't know if
Yeah.
I'm pronouncing that correctly. MANGA
Mhm.
Firefly Value Added Catalog, a catalog of 3.7 million spatially resolved stellar population properties across 10,000 nearby galaxies from the final data release of the survey. Um, so two questions. So this seems the scope is very big, 3.7 million spatially resolved stellar populations. But what is sort of the objective of the survey, or objectives, I should say?
Yes. So MANGA, which is mapping galaxies at the Apache Point Observatory, is an American mission, actually, based on the Sloan telescope. And when you have a galaxy and is very distant, you essentially collect the integrated light, the sum of all of it, which looks like a point or a small area. But if the
Yeah.
galaxy is nearby, it will cover an area. And then, instead of only obtaining the global property as we can do at high redshift, you can actually scan it like if you
Mm,
were like people. Again, we use this analogy, X-raying the body of a
mm,
person. You actually go through with your spectrograph through the various slices of the galaxy. And in
mm,
this way, you can actually pose a very strong constraint to galaxy formation by obtaining the radial properties. So not just the
mm,
total mass, but how the mass vary with radius, how the chemical composition, so the metallicity, vary with radius, which then will suggest how star formation has proceeded in those galaxies. So this
mm,
MANGA experiment is one of the largest survey of local galaxies. So this 10,000 means you collect everything that is in our local universe, which contain
so
elliptical
local, sorry to interrupt. So local means like very, very low redshift, like less than one, less than
galaxies.
zero point 0.5,
Oh, much less than one is
much
0.50.
less.
0.50. Yes, you needed to minimize those corrections that we spoke earlier. And
Yeah.
essentially, not exactly not to have any type of this effect, but look at the universe. So in our neighborhood, 14 billion years after the evolution, what do we see? This is a
Mm,
study of the galaxy population, and there are differences in morphology. For example, do we see spiral
mm,
galaxies? Do we see elliptical? This is a science that many colleagues have done for years. What we do further in this manga is to look inside each of these galaxies
mm,
and then applying the same model and sophisticated spectral fitting, like it is a theoretical model matching to data, and the name is Firefly, something we have done in Portsmouth, that fit every bit of the observed spectra to the same bit
mm,
of the theoretical model. You can actually make a conclusion on how things work and how they form. And then you have
mm.
a view of galaxy evolution here at this epoch.
Yeah.
And then you need to extrapolate back in time to
Mm.
understand really how were these galaxy doing 10 billion years ago.
Yeah, it's like you found a local school where there are a large number of students,
Yeah,
and you can go study them, and make some, well,
yeah,
you could speculate, what the students are going to do in the future, so to speak.
yes.
But the full spectral fitting code, Firefly, is employed to derive parameters such as stellar ages, metallicities, stellar and remnant masses, star formation histories, star formation rates, and dust attenuation. So that seems like, if I understand this correctly, Claudia, I don't think I do. Um, there are two objectives here. One is to say, let's go collect data from the local school, and we can then analyze that data. We can make some predictions, and then we can use those predictions to look further out than the local school. Is that the way to think about it?
Perfect. Actually, it's perfect. And you want to think, okay, if in the local school there is this very group of students with this characteristic. How did they come to be?
Yeah.
Right. And that's the pattern. And for galaxies, we call radial gradient in chemical composition, but also age. If we find that galaxies are mostly old, well, then we need to assume they started to form shortly after the Bang. If we find a pot of quite a young object, so we need to explain how they form in an expanding universe. So exactly that. The thing is, you picture it so well. The question in the school we would have, is the school representative of all? Yeah, and we have the same problem in galaxies. Because, for example, in the local vicinity, we don't have very massive galaxies. They go out, we need to go back in time to see them. In the local vicinity, we are lacking those. So in that very survey, our most massive galaxy is some 100 million stars, so 1 billion and so on. But we lack the very massive one.
We lack the variety. We lack the cross-sectional depth, so to speak, right? So, but I think it's instructive in some ways, isn't it? I mean,
yes, no, it is still very instructive. For example, the chemical composition, that is a notion that has impressed you. We noticed that there is an anti-correlation between how big the galaxy is and their chemical composition. And the most massive galaxies are more metal enriched. Then small things, dwarf galaxy, can be very, very metal poor, so devoided, with having some elements, but just a little bit.
Is Firefly your code?
It was actually the project of a past PhD student of mine.
Okay.
He gave the name, yes, and I was the supervisor. And we, of course, he did most of the work in Python, which is not my language, but we constructed it. But it is a publicly available routine. Everyone can use it.
Yes, my intuition tells me, without knowing anything about it, my intuition tells me the outliers could be quite interesting. Which is, so suppose, we have some expectations when we look further out and we find something completely off base, so to speak, from those expectations, that could be a good candidate to further study, right? Because maybe we missed something, maybe there's something else out there.
I'm very impressed by your intuition. What you say is the astrophysics of the outliers, or called strange spectra, was one of the first projects that someone put after this survey started to operate. Instead of looking at the well-behaved spectra that fit the model very well, this group researcher, I think they were based in Brazil, they were actually hunting for weird spectra. And they, in some cases, these are observations. They may look weird because there was bad weather. These are telescopes on the ground, right? So you need also to have those effects. Or they may be intrinsically some deserving surprises, and some things have been discovered that way. The thing is that, as again in the Heisenberg principle, you have a model, and essentially you can find things within that model. And that's how Firefly, who is a very free code in the sense that we minimize really our prior, but still, if you put an age that goes from 100 million years to 15 billion years, every galaxy that you model will have an age within that grid. If you're able to extend the models, then you will find other things. That's intrinsic.
So the model is predictive. So you can use the model to say, suppose I look out 1 or 2 redshifts out, I could make a prediction from the local observations.
Absolutely. This is an output that we have automatically with that code, because each galaxy that we analyze will be consistent with a certain history of star formation, we say, which is the fraction of the mass that was built at various epochs. And that gives you a straight prediction with redshift, because epochs, cosmic epoch, means a redshift. And then you can say, okay, this galaxy started to form a redshift 5, formed 40% of their stars, did nothing up down to redshift 3, then had another burst. And so this is the topology of star formation that you find. And it's very nice to analyze all those files. There is a lot of output, as you will say, 3.7 million spectra in all the galaxy. And each of them will have all this output, but it's an amazing project for students, which we keep proposing, try to mine into those databases.
So I don't know much about this, Claudia. So, but there was some talk about. So we talk about this expansion rate of the universe, but I saw some papers that sort of talked about there is no expansion rate of the universe. The universe is expanding at different rates. When there's a cosmic void, maybe it's expanding a lot faster than very concentrated areas. So is this going to throw a wrench into, or not a wrench, but is this another parameter you have to consider when you sort of look out?
Well, this is a very good question. In reality, these models are based on the evolution of stars, and in principle, they are independent of those values, which in general, in the 70s, I want to acknowledge Beatrice Tinsley, who actually put down the framework of the model I use. And she thought, in fact, because we're using nuclear burning that is subjected to quite a well-known physics, we can then use the to set constraint on this big unknown that are the cosmological parameters. Because obviously, the age that you mentioned earlier is a fit to the cosmological parameter, but the stars in the galaxy will give you a real age, because it's essentially how long it takes to finish the hydrogen. And so in a sense, you can then constrain back the actual age of the universe. And now there is a strong debate with the James Webb Space Telescope results, because several colleagues are finding galaxies that are quite old for the epoch they are found, which is very close to the Big Bang. And this poses a cosmological problem. Are those ages really correct? Then how is it possible to form a galaxy so quickly when there was so little? Or you can say, well, the galaxy ages are correct, cosmology is not. And so there is a lot going on right now.
Yes. Yeah, I'm just holding out hope that lambda CDM would be replaced at some point.
Well, it's fantastic what you say. The big crisis happened in March with these DAISY results. Let's see what the Euclid's results will say on the same. But lambda is one part of this cold dark matter model. Let's see what happens.
It does remarkably well so far. So you have another paper here, candidate massive galaxies at C of approximately 4, redshift of approximately 4 in dark energy survey. So you say here, using stellar population models, we predicted that the dark energy survey, DES, due to its spectral combination of area and depth, would be in the position to detect massive 10 to the power 11 solar masses, galaxies at approximately redshift of 4. We confront these theoretical calculations with the first DES data reaching nominal depth. So what do you find? So you have some theoretical predictions, and you find something different from the data, or you're sort of confirming?
No. Yeah, fantastic. So the dark energy survey is one of those cosmological surveys to constrain the lambda in the lambda CDM. But cosmologists need a huge amount of data in order to make their signal robust against systematic. In that huge amount of data, what we thought and we put forward in that paper, there are going to be some very high redshift galaxies. The clue of that paper is that it was made before the advent of the James Webb Space Telescope,
Yeah.
which finds now a lot of distant massive galaxies, but we did find them before. Redshift 4, which is very near the Big Bang, very near to this fantastic redshift that James Webb is actually sampling, but they are very massive. Okay, and we found them in a survey that is essentially optical, without a space telescope. This is what I mean. Through stellar population model, making prediction. But what we do also in this paper, we actually compare the abundance of these objects normalized to the prediction of cosmological simulations based on lambda CDM. And what we find, and that's similar to what the James Webb Space Telescope work find now, is that the lambda CDM struggle to predict that large amount of massive objects. For the simple reason that lambda CDM is a hierarchical model. So initially, it is mostly composed by small mass objects, which then merge together to give you largest object. And this takes time. And that's the, and we found them at Redshift 4, which has a very distinct cosmic epoch. In that paper, around 250 of those objects, which we could compare directly. The key, this is what we found.
So Redshift 4, what is sort of the horizon we are talking about from Big Bang at Z of 4?
It's roughly 2 billion years since the
2 billion years, okay.
Yeah.
And
that came about due to the characteristic of this of the dark energy survey photometry, in the sense that how far you can go in redshift depends also on the span or wavelengths of your data. And of course, how many photons can be collected by your telescope. And in this, the James Webb is absolutely king. But we could do something with that survey, which was a way of us for exploiting, making sense of this expensive experiment. And so the redshift that we could actually probe is around 4, but it's a very respectable redshift.
Yeah, so my ignorant perspective is that if things are dynamic, if things are changing over time, then we cannot really neatly fit a regression line on the data. And so are we missing something in any way, or what's your intuition?
No, so those type of stellar population models allows you, and that was the cosmological clue that Beatrice Tinsley included in the thinking, a time variable by which you can evolve them back in time.
So you can fit a nonlinear function to it, so
absolutely, to speak. Strongly nonlinear, because the evolution of the youngest population occurs at very high energetics, and then they decay and they settle to a much smaller emission. You don't fit a line in these things. You have a strong nonlinear evolution. That's the aging of the population. But in general, the prediction is actually robust. You will know how a young galaxy should look like, and then you look into the data. It's not that everything works, as we know, and that's why we keep. There are many lines that remain unexplained. There is the possibility that is actually a reality, that most stars are not single but are in binary systems, and that give you other features. So it's a tough science, but it's a beautiful exercise, because you have to
yes.
model and you try to match them. It's very satisfactory.
I love it. I wish I got into it when I was young. So you finish up here. This is an ideal sample for spectroscopic follow-up to select the fraction of galaxies which are truly at high redshift. These initial results and those at the survey completion, which shall push to higher redshifts, will set unprecedented constraints on galaxy formation, evolution, and the reionization epoch. the little that I know, what is the highest redshift galaxy we found from JWST so far?
Well, 14 something,
14.
16. Yeah, but the 16 was revised a bit, so 14, but it's incredible. Incredible.
And that wasn't expected, right? That's too early, isn't it?
That is a very good, well, we have, so I don't belong to those that were completely surprised. I was pleasantly surprised. If I look into our own Milky Way, the globular clusters in the Milky Way are 14 billion years old. They are as old as the universe. They are very old, whatever model you put on it. That's why, to say the least, we should have found those clusters. Now, their mass is not very large, and therefore, we cannot actually think that it's only those clusters giving us those light. It has to be actually a galaxy. Now, this is really pushing our knowledge of formation of galaxies, which we all grew up in this lambda called dark matter. We needed a bit of time to boost these fluctuations.
Yeah.
However, we see this data. Now, as we said all in this podcast, the actual properties of those galaxies completely depend on the models used to analyze them. And therefore, we all should allow a little bit of leverage, because if we put another model, that age and that mass can change. We are actually going to try to see how much that dependence is giving us any sort of hint to the actual evolution of galaxies. But it remains that James Webb has found very luminous lighthouses right at the beginning. And that's very exciting, I tell you. It could have been all dark, and it is not.
Yeah. All your students and all the young kids possibly listening to this, this is a fantastic area to get into. Every morning that you wake up, there are more interesting puzzles.
Exactly.
That you could go after. There are very few fields that, well, life sciences might be one of them, but very few fields that would give you that level of flexibility. So I want to finish up with your another paper, stellar masses of SDSS 3 and BOSS galaxies at redshifts of approximately 0.5 and constraints to galaxy formation models. So before we get into this, so could you define what SDSS is and what BOSS might be?
So SDSS is the Sloan Digital Sky Survey, which is a very American project funded by the Sloan Foundation. Jim Gang is one of the patrons of it. The telescope is in New Mexico, and since over 20 years, it has collected data because it's a private telescope, so it's fantastic. It just operates with some refurbishment. So the Sloan Digital Sky Survey is one of the massive projects that exist in astronomy. And what happened was that one of the co-founder of the astrophysics group in Portsmouth was a member of the Sloan, so he brought all this data into our university. So we became the first UK full partner of the Sloan. And what is the value? The amount of data was the largest, still is. So that's SDSS. Now SDSS has a series of projects, SDSS 1, 2, and 3. This is the third edition where I did this paper, which is very interesting. I will tell you why. And that focused on actually the cosmological motive was to probe the imprint of the baryon acoustic oscillation, which is a signal due to the expansion. But for doing this, 1.2 million galaxy spectra were collected. So what we have done in that paper, we used them for the galaxy evolution part, where we are experts, to try to see how did galaxy look, and I'll tell you what, at the epoch when the sun was formed. It is a very interesting epoch, one of these coincidences, because it's at the same redshift where the Nobel Prizes now have found that the universe accelerates the expansion. This is very similar. And so what we did in that paper, we look at the most massive galaxies and we tried to find whether they were different from their counterpart in our local neighborhood. And they were not at all. There was no sign of evolution over the past roughly 5 billion of years. And so that's interesting, right? Because the universe in the past 4.5 billion years started to accelerate the expansion. However, the galaxies have remained as they were. And this is interesting also philosophically, if you like, considering the epoch at which. That's the clue of that paper.
So as you say, we perform a comparison with semi-analytic galaxy formation models tailored to the BOSS target selection volume in order to contain incompleteness. The abundance of massive galaxies in the models compare fairly well, you say, with the BOSS data, but the models lack galaxies at the massive end. Moreover, no evolution with redshift is detected from 0.6 to 0.4 in the data, whereas abundance of massive galaxies in the models increases to redshift 0. Okay. Do we have any galaxy with a redshift of 0? There is one, right? There's a small one that we found.
Yeah. So there are galaxies with redshift 0, at redshift 0, not that the mass. But that's the volume that is covered. So we live in a cone. We are here, right? At the vertex. And the universe goes there. So the more we look back in time, the more the volume increases. So the likelihood of finding this galaxy is larger. And that's why this intermediate redshift, the 0.5, was perfect to our purposes. But there are some in the local universe. And if you compare the prediction of these models versus the reality, there is something still that needs to be found. Okay.
Job security, there is still a lot to be found, which is a good thing, I would imagine. Go ahead, sorry. No, so I was just going to ask you, so you're doing a lot of research in this area. I mean, this seems very, very rich. To look at galaxy formation, you can look out at different time scales. You can look at different types of galaxies and different formation patterns and techniques. So based on all the research that you have done, what is your intuition? So we have, we have lambda CDM, we have inflation, we have some theories sort of floating around, I would say. Well, I'm not a physicist. It seems like they're floating around. What's your intuition? Are we pretty close to reality, or do we have to do something dramatically different from what we have done so far?
Fantastic question. I keep changing my mind because, in a sense, this brilliant idea of a lambda CDM universe in a Big Bang model, I strongly believe Big Bang, the origin and the pattern of elements, because the probe of it, the Big Bang nucleosynthesis, is incredibly precise, and that works very well. And the simple fact that the more you go back in time, the more actually galaxies become younger, and that's really is a testimony of this type of imagination of an origin. Now, the dark matter, I would hope that we can find what it is. If you think about, I started studying I have a PhD obtained in '98 when the dark energy was discovered, essentially, and now all these years afterwards, we still have no idea. So we keep using this notion theoretically. It works very well. So in this sense, the answer to your question is yes, we are quite close to reality, but we are close to reality with an ingredient that we don't know what it is.
Yeah.
So as a physicist, the physicist in me really would hope, would fund this experiment to try to find the actual particle that we call dark matter. On the other hand, Gill, this James Webb Space Telescope recent results tell us that the time may be running a bit different very near to the Big Bang, because we find these monstrous objects that they are there, they shine, then they evolve at very high epoch, and it's incredibly interesting. So yes, I think we are close to reality, but considering the very last few years, the door may be open up with a new surprise for all of us. So it's strongly motivating to go to the office these days.
Excellent, excellent, Claudia. Thanks so much for spending time with me late in UK. Really enjoyed the conversation.
No problem at all.
Thank you.
Thank you very much.